Who first shared their stories in caves? Connected art, nature, and science led us toward new horizons. Who thought to capture motion? Spark an engine to life. Turn television into a playground. Every day, you create the playful, the functional, and the unexpected. You break down walls and take us to astonishing places. Tell stories, leap borders, and create beauty for tomorrow. Because at Unity, we believe the world is a better place with more creators in it, where everyone has a chance to shape the world.
Good afternoon, everybody. Welcome to our SAPAC 2021 series. I'm just going to pull up my slide deck for a moment. Bear with me. Okay, welcome from a very diverse region, from Greater India through to New Zealand. We do these webinars every week, and a few reminders of interaction points in the webinar today. We will probably try and drag out the intro a little bit. We've got a bit of an issue with some people connecting via Zoom today. So please keep all question and answers to the Q&A box. We only use chat to post links and resources, or if there's any quality issues with the webinar. And the raise hand function is not used in this webinar at all today, so please refrain from using that. Complete the survey at the end of the webinar, go into the draw for a chance to win a Unity swag pack. We will post that towards the end of the webinar around Q&A time. And just a reminder of our webinar schedule for November and December. We're going to stop the 10th of December for this year and rejoin you in February, but some really good topics still to come for the rest of the year. And of course, today we are bringing to you the use of synthetic data for computer vision model training. And we're joined today by our colleagues from Canada and the US, Washington State and Alberta. And Kevin, if you'd like to take away today's topic, please.
Great, can everyone hear me? Cool. Thanks for the introduction, Andy, and thank you all for taking the time to join us for our computer vision and synthetic data webinar. Alex, do you want to start the slides? Ooh.
I am starting. One sec. Yep.
All right, there we go. All right. So as Andy mentioned, oh, gotta go up. No fast forwarding. All right. As Andy mentioned, I'm Kevin Saito, and I'll be kicking things off for us today. For our agenda, two slides forward, Alex. There you go. I'll start with an overview of computer vision, and then highlight some of the advantages that synthetic data provides. Then Alex will talk to us about how you incorporate synthetic data into production systems that are largely based on real-world data. And then he'll take us through a couple of relevant case studies. Then Salehe will do a preview of some of the research we've been doing around synthetic humans and synthetic data. And then Alex will help pull it all together at the end by walking us through how to create a synthetic data generator. All right, next slide. So at its core, computer vision is a process of teaching machines to understand what it sees, typically for the purpose of taking a specific action. And due to the decreasing cost of compute and sensors, we are seeing proliferations of smart sensors, which can take simple actions based on what they observe. So tasks can range from things like counting an item on a shelf to more complex ones like detecting or identifying objects in the path of an autonomous system. Okay, and so when you look at how to train a computer vision model, the reality it's a lot like how a young child learns, right? So just think about life as 60 seconds of frame of data, 60 frames a second of data. So just like a young child learns to identify its parents based on countless interactions, machines can learn to identify items through lots and lots of data. And today we'll talk about how synthetically generated data helps solve the data problem. Okay. Next slide. So traditionally, as many of you know, training for computer vision systems has been gathered in the real world. However, as customer use cases expand, people are quickly finding that real-world data has certain limitations. For one, gathering it is typically a little expensive because you need to send someone out to the real world to gather the images and whatever those costs are associated are. And two, the process is actually somewhat time consuming. So once you gather those images, you'll need to send it to a firm typically to label and annotate, which, from talking to partners, the single training cycle relying on real world data for gather and annotate can take up to 6 to 8 weeks, which dramatically lengthens the loop of any of your training cycles whenever new data has to be gathered. Okay, third, because of the expense and time required to get the data, what you will almost certainly be left with is a certain amount of bias, as the costs required to make it impossible to generate a globally diverse data set, which means your models will be subject to the bias of the region, the time of day it was captured, or any specific location-specific characteristics, making it potentially inefficient at dealing with some of the higher variation scenarios in different locations, as an example. And then lastly, this is actually becoming a more recent, growing concern. Google and other folks have told us that because of increasingly stringent consumer privacy laws that give users greater control of their data, many companies are finding that previously gathered data may no longer be privacy compliant. The net result of this is, if a consumer opts out of their data being used, companies are technically required to remove that data from the data set, then rebuild the entire ML model from scratch, which is incredibly expensive and incredibly time consuming. And then to put that all in perspective on the next slide, let me walk you through this in the context of the typical computer vision workflow, right? So as we mentioned, the way this all starts on the left in number one is, time is spent to sort of gather and annotate these images. So you acquire the real world data, you label and annotate it. We've heard from companies, depending on what you want to do and the scale that you're doing at, the cost to annotate could be anywhere from 70 cents to $3 a frame. And in addition, there's often costs associated with each bounding box that has to be drawn, or any additional label that has to be applied, right? So once 1 and 2 are done, you then use this annotated data to train your CV model, then you evaluate the model, and the result is either you deploy the model to production, or in reality, the most likely scenario is you're required to do another iteration because of something that you find out as far as in the training cycle, which is why most real world models are spending roughly 70% of their time in steps 1 and 2, which is acquiring the data and labeling the data. And this is where we're sort of investing our efforts around synthetic data. Okay. So obviously, the challenges of all of this is, the point of all this is we're pointing out this relying solely on real data comes with both data collection and data labeling challenges. And we've talked about the key data collection issues at the top. But what we've been learning more recently is there are also issues associated with data labeling, right? So in surveying, the market of data labeling firms, they'll typically claim 85% to 95% accuracy in terms of their results of labeling, which means roughly an error rate of 5 to 15%. MIT found that errors in the data labeling translate to a slightly more than linear impact on a model accuracy, meaning a 5% error rate leads to roughly a 6 to 7% reduction in the model accuracy. That said, in a separate experiment, they actually went back and fixed all the errors, and they found the optimal model for the data set changed, which is actually much more impactful. And the reason that they concluded for this was human labeling errors are more systematic than they are random, which makes a lot of sense if you think about it. For instance, if we have two individuals like Bob and Joe, if Bob thinks A is B and Joe thinks A is C, then the prevalence of the labeling error will be determined by the percentage of labeling of an item that A was done by either individual, as an example. All right, so this is coming down. The other thing that we're seeing, next slide, is in addition to all of these issues that we cited, is we're seeing a greater need for labeling scenes of increasing complexity. For instance, let's take an image, the one on the left, it just has cars, roads, buildings, and crosswalks, right? Pretty simple. This image is obviously pretty easy to collect, but what we are seeing is customers' needs to get more and more information out of the task that they're trying to train their CV system for. Expands in scope and complexity, as an example. For instance, if our task was to understand how many cars go through downtown, for example, we need to identify the number of cars within the image and draw bounding boxes around the 1, 2, 3, maybe 4 cars that you see in the scene, right? Take the same image, but let's say our task is now to understand how many people use a specific crosswalk. Now we'd have to count all the people, some of which are actually partially occluded by the car, and even potentially partially occluded by each other as they're sort of walking like this. As a result, now you actually need to do more of an instance segmentation, which is much more expensive, as you have to go pixel by pixel around the outline of each person, right? And this is sort of the complexities that we're seeing that's leading to increased costs and scenarios that you're seeing for real world data. Okay, next slide. Now, given that there are actually a lot of scenarios where their real world data just isn't even practical, right? So, for instance, the scene on the left, we see the crowd in this sort of crowded public space. Whenever you have a situation where you have lots of assets that require labeling or lots of background labeling is required, you have a problem because one, you can only really label the assets in the front, meaning the humans in the foreground, because your labeler will have difficulty creating distinct bounding boxes of anything moving into the background. In addition, the number of items or the number of people in this scenario would cause the cost of labeling the scene to be actually quite expensive. You can probably guess there's probably maybe 100 or more people in the actual image. And then the practical reality is once you move past the first, third of the frame, the back third of the frame, some of the individuals might only be 10 or 20 pixels high, which makes it very, very difficult for any human to do any significant discernment. The second scenario you see in the middle is a school bus. And this is a project that we are doing for a customer. Now, they can actually identify the school bus quite well, but what they cannot identify so well is that stop arm that you see coming out. And that stop arm in the United States comes out when a school bus comes to a stop to pick up or drop off students. So this happens relatively infrequently when the school bus is driving around and only in certain areas. But the reality is when that stop arm comes out, and this is why it's important for the customer, is vehicles traversing in the opposite direction must actually come to a full stop. And if you're coming the same direction as the school bus, but just one lane over, you would also be required to stop. So this is a very specific action that occurs very infrequently and only two times a day, pick up and drop off for the school bus. So if the practical reality is getting this data in real life is actually quite difficult. So the real life observation rate is low. Hence, they are actually turning to us to use synthetic data to generate these types of scenes and fill out the gaps in their data catalog or in their database. And the last one, whenever we have situations where the variational difference is very subtle between the items. So if you look at this, if you're asking your annotator to label the cars, that's not a problem. If you're asking your annotator to find the Tesla, only label Teslas, that's probably okay. That's a relatively distinct vehicle. Anything more than that, like asking them to pick out the Nissan Leaf in the group or the BMW i, this is where it's going to get tricky, right? So the challenge is whenever the differences are subtle, the human annotator potentially could struggle to actually pick up the differences and appropriately label them. Okay. So what this all comes down to is how do we do things differently than the traditional computer vision workflow? So the traditional computer vision workflow on the left, you see the typical acquire, label, then you validate the images, and then you take time to deploy, and you see a time of maybe like 3 to 4 to 5, 6 months, depending on the cycle time for each specific step. For our situation, what will happen is you create the synthetic environment. We will accurately label and you do everything using synthetic data, which means there's no actual hand labeling annotation. It's model gets created, the data is generated, everything comes back with perfect pristine labels and images. So that's all done perfectly for you. And the cycle time, once you build the initial project, is not weeks or months and you do a full data gathering loop. It's typically days or maybe 1 week at the tops. This is what allows our synthetic data approach to be much more effective, much more timely, and drive a fast iteration cycle for you. Let's put that into sort of images. And in reality, what does this look like? So this is a typical scene. You see us just generating various types of images. We apply various either 2D or 3D bounding boxes, do semantic segmentation for various items. And in some of the scenes, you actually have the ability, we show the distance between items. Because one thing we can do with Unity is apply a higher level or a much more sophisticated metadata layer to the labels. We can tell you the distance between things. We can tell you the size of things as an example, because we know where everything exists in the scene on X, Y, and Z coordinate space. Okay, the next slide. The other thing, the other way we do that, we sort of drive up the amount of data you can get and help scale your data set in very, very efficiently, is we use a concept called domain randomization. So for instance, on the left, we take a typical scene, and what we can do is vary the background, the lighting, or any types of components that could affect the way that item is perceived, right? In addition to that, we also get to what they call a naive placement strategy, where we just take a single item, if you're looking to do object detection, and we rotate it. So take a picture of it from every angle, as well as put a random set of things in the background that basically force the model to learn how to identify something generally in any type of condition, regardless of the orientation of the point of observation or the item itself. And all of this basically allows you to build a model that is very, very resilient and allows you to generalize what is object recognition in all sorts of circumstances. Okay. Next, let me pass off to Alex to talk about how we apply synthetic data to production systems.
Thanks, Kevin. Just a quick introduce myself, Alex Stamen. I'm the senior manager in the computer vision product team here. Gonna dive a bit deeper into what we're doing with synthetic data and some use cases that we've worked on with customers and some things we've learned along the way. First thing I want to talk about is really what is the problem we're solving here. So the problem we're solving is when you have an AI application that you're trying to deploy in production, there's a certain quality of service that you'd like to guarantee, or at least have an understanding of what are the conditions in which it works. When does it maybe not work so well, but I'm okay with that. In terms of pre-production on these models, as in while you're building them, a lot of times challenges you encounter, differences between the data you are using for development and the data that is actually in the field. And we're actually going to talk about a case study that had a situation of that. Edge cases, things that don't happen very often. Selection bias, your ability to collect the data or the data that was collected to kind of bootstrap your model might have been biased in a particular way based on the criteria you used. In post-production, model drift. Hey, the world changes as time goes on, and you have to keep refreshing data. Survivorship bias. This is one that really is painful for any application that has like a user experience associated with it. What ends up happening is the things that don't work well, people stop using those features, or that population stops using it, and your model starts to work even worse because you're incorporating data only from the data you're collecting. But if the people that it doesn't work well for drop out, then you lose their data. So you kind of optimize only for the things that already worked well to begin with. And what we were looking at in terms of synthetic data and how we want to apply some of our techniques is we really want to help your model generalize. Looking at synthetic data, not just in terms of adding more real world like data to our data set, but like how can we look at the entire problem start to finish, and how can we leverage the power of synthetic data, which is perfectly labeled, free of some of the other concerns you talked about, and programmatic being a very big part of this. How can we harness that power with your entire ML pipeline and get your model to generalize better, which should help you both in pre-production and post-production quality of service. You heard Kevin talk a little bit about domain randomization. Just to briefly touch on this here, and this is like by no means an exhaustive study of the topic, but just to give you an overview, domain randomization is really about randomizing your data set relative to the domain that you're targeting. And I put a couple of resources on here if you want to read about this later, but some things that they found is when you're doing synthetic data and you're doing domain randomization, the things that you perturb in the environment do not actually have to be realistic. And this is why you see, and you will see a lot more of this when Saleh takes over, some semi-weird looking imagery. And realistic, and what we're finding is that, assuming you vary your data on the right dimensions, this actually helps you significantly in overcoming what we call the sim to real gap, teaching the model to build domain invariance, as in, if you're doing object detection, primarily the background of a particular object detection use case. So let's say it's a grocery store, detecting items on the shelves. The shelves aren't adding a lot of information for you. So what you're really trying to do is teach the model that information doesn't even matter at all. There's some well-known research on domain randomization. Again, not an exhaustive study at all, but just three fairly good papers to just kind of give an overview of it. One from OpenAI that's focused on kind of a robot arm picking up blocks on a table. Another one on autonomous, that's like an autonomous driving type scenario from NVIDIA. And then the last one is one where is actually a very interesting one where they actually trained a fairly well-performing object detection model for grocery store-like objects, almost exclusively on synthetic data. And what we are seeing, and this is kind of directs a lot of our focus, is that large data sets of highly varied synthetic data, plus a small set of real-world data is really what produces the best results. So the idea here is you might still require some real-world data when you incorporate synthetic data, but your need for how much diverse real-world data that is labeled that you have to collect should go down significantly and be replaced with much larger sets, and then help you generalize better along the way. A couple case studies. This one is public and you can find it online. NeuralPocket, a customer we worked with. They have a couple of different detection type models that they were building. But in terms of bootstrapping it, they had some tight timelines and they really needed a way to start bootstrapping their models and get them into production for a couple of different scenarios. They have some things around detecting potential security threats like knives and guns from CCTV type footage. There's also some things about detecting objects such as devices that people are holding, like smartphones, and people as well. They actually found, their costs were quite high, right? So they take on these projects. They typically had to do like 30 training cycles at about 60 to 150K, and it took 4 to 6 months per project. Here's kind of an example of like, actually, they followed this kind of domain randomization approach using some of the work we have done. And what they found is, now this is on a fairly limited data set, but this is actually what they had to bootstrap with. They actually found a very significant improvement in their test data set by just incorporating synthetic data from Unity, using some of the strategies that we've been recommending and working with customers on. Okay. Again, still a limited data set. However, this got them much further towards something they could start getting out into production and getting production data from much faster than before. Autorate, this is another very interesting use case. They are building an automated way of reading COVID tests. And one of the challenges they have, so that, imagine this, like they've got a mobile application, and the idea is you hold up a COVID test to the camera, and in real time, they can actually read the positive or negative result. And they can process through these tests quite a bit faster as they come in the labs, right? Well, a couple of problems that they had. Well, COVID tests were changing once a month. Every month they would get a set of new kits. It's not even just one new kit. It's a multitude of new kits from the manufacturers, plural. And each time they were doing it, they were having to collect new data. Well, that's just completely non-scalable. Because then it's like, well, then, you get new kits in, there you start at the beginning, I got to collect new images, get them labeled, build my model, test it out. Other problem is where they were getting, when they acquire these kits at first, when they're delivered to them, they have to, in the early stages, they actually have to keep these in these biosafety labs, which have no windows, so no actual exterior lighting. They go out in the field and they try to actually test the application in the field. Well, the pharmacies or the different labs where they're working in actually do have real windows. So they're getting outdoor lighting. So they actually found a lot of different shadows and lighting conditions between the training data they were collecting and when they actually had to deploy that application into the real world. This is kind of what it looks like. Effectively, they were doing object detection to find to sort of like segment out the parts of the kit itself, which again varied by manufacturer. And then they would do a classification algorithm for just reading the particular test strip. And as you can imagine, these test strips, I don't know how well you can actually see it on here, but they don't just cleanly come out as like a solid line or no line at all. Sometimes there's faint lines. Sometimes the line doesn't go all the way across. So it's actually a bit of a challenging one to really get a good set of data on, because you just have such a diversity in what you really need to detect here. So what they did is they ended up moving to having an artist effectively, once they get the kits in, quickly create a sort of digital version of that test kit. They have, working with us and some of the tools we provide, we're able to build what we call a data generator. that allows them to insert that test kit in and very quickly randomize the environment, randomize lighting, blur, backgrounds. With the test strip, that was actually also done using a procedural system to actually generate procedural test strips. And they did a large number of randomizations around how faint and how complete the lines were, and sort of some other, like, you can imagine as like noise characteristics. What they found was by taking this approach, they were able to match the performance of the real world data set with using 4x less real data. So imagine before they were just using real world data, and they've incorporated synthetic, but now they're going down to a very small amount of real world data they're incorporating. And only 8,000 synthetic images for this use case, which is actually quite small. But a really important part of this was synthetic data, or the models trained on synthetic data, were more resilient to adverse conditions. So the things like when it goes into the real world and I see new lighting conditions that I did not have in my training data, it is now more resilient to those adverse conditions. So if we go back to the idea of we're really looking at quality of service in the real world, pre and post-production, these are the types of post-production challenges. And we believe with synthetic data, and we're seeing from customers, if you apply this to your model, you really actually can guarantee better quality of service once you get out in the real world and the conditions are different. And with that, I'm going to turn it over to Salihi for a bit to talk about a particular research initiative that we've been working on.
Thank you, Alex. My name is Salihi Abadi. I'm a senior machine learning developer at Unity. I'm going to talk about People Sense People. It's a data generator for a few human-centric computer vision tasks without needing real-world human data. That's why we call it People Sense People. That means we do people tasks without using people data. Next slide, please. So in recent years, people detection and human pose estimation have made great strides, mostly helped by using very large-scale labeled data sets. However, these data sets had no guarantees or analysis of human activities, poses, or context diversity. Additionally, with human data, privacy and ethical concerns may limit the ability to collect more human data. An emerging alternative to using real-world data that alleviates some of these issues is synthetic data. However, creating synthetic data generators is incredibly challenging and prevents researchers from exploring their usefulness. Therefore, we created this human-centric synthetic data generator called People Sense People, which contains simulation-ready 3D human assets and a highly parameterized camera and lighting system that is complemented with domain randomizers. So here you can see a few examples of the data sets that we generate with People Sense People. As you can see, it's highly diverse and kind of psychedelic looking. And at the bottom row, you can see the human key points and 2D bounding box labels that we were able to obtain with this data generator. Next slide, please. So here I'm showing more examples of People Sense People. As you can see, we have high diversity of looks for the scenes, high diversity of textures, colors, post-processing effects, camera perspectives, camera intrinsic parameters, and also we have varied poses for our characters, varied clothing textures, and a whole lot of diversity. Next slide, please. I don't think I can see the next slide. I wonder if it's been switched. I can see slide 26.
Yeah, I've got 27
Right,
up. Is it not coming through?
Perfect.
Okay.
Yeah. So yeah, as I mentioned, People Sense People provides a set of 28 parameterized simulation-ready 3D human assets. I think we're switched back to 27 right now. Yeah, in 27, I'm showing more examples of our generated data sets. As you can see, we have really large close-ups of people and then wide angle views of the people. So we get a large amount of diversity in our data sets. We have 28 parameters, simulation-ready human assets, 39 diverse animation clips, and roughly 22,000 unique clothing textures, which I'll explain in a bit. We have parameterized lighting, parameterized camera system, natural backgrounds. We use primitive objects as occluders and distractors in the scene that help us train a more performant model by occluding parts of the people. And we build everything into a Mac OS and Linux binary. So you don't even need to install Unity. You can just run the Mac OS and Linux binary and generate really large scale data sets very quickly. Next slide, please. So what computer vision tasks can people, sense people target? Here I'm showing on the left the image, and the next images show the human 2D bounding box and human key points, also human semantic and instance segmentation. We're also able to obtain 3D bounding boxes. For this work, for this research that we did, we used only human 2D bounding boxes and key points. Next slide, please. So, as I mentioned, we create a highly parameterized environment dataset generator. This is complemented by using a set of domain randomizers. Our first set of domain randomizers are for objects. So for 3D objects in the scene, we can vary their placement, we can vary their rotation, their scale. Also the same thing for the foreground objects. And for people, we can vary their animation or pose. For the textures and colors, we're able to change their actual texture and hue. And for clothing textures, we can change their albedo, normal, and masks as the simulation progresses to obtain even more diversity. Next slide, please. And as I mentioned, we have a parameterized lighting system, so we can move the lights around in the scene. We can rotate them, we can vary their intensity and color. We can mimic the time of day of the year, and the latitude of the sun, basically. It's the time of the year. And also we have a parameterized camera system that changes the position and rotation of the camera, as well as some internal camera parameters like field of view and focal length. We also have some post-processing effects that we can apply to the images that get rendered, such as vignette, exposure. We can change the white balance, depth of field, and some color adjustments such as contrast and saturation. Next slide, please. So to put this in perspective, it's good to compare this to a large-scale real data set. For this task, we use the COCO person data set. It's a data set of roughly 64,000 training images with 2,700 validation images. As you can see in the table below, for our synthetic data set, we generated a data set of 500,000 images. And we divided that into 490,000 training images and 10,000 validation images. As you can see, we have per data set, we have much larger number of instances. So each instance is basically a person bounding box. And per instance, we have more key points annotated in our synthetic data set. Next slide, please. So if you were to look at what the bounding box placement of people looks like. If you remember from a few slides ago, where we showed the people placement, you could see that they were scattered in the scene. That is caused by uniformly sampling object placement within a volume. So if you were to take all the bounding boxes that we generate for people and overlay them on top of one another in an image frame, this is the kind of heat map that you can get for COCO and synthetic data. As you can see for COCO, everything is so focused in the center. That's not surprising because most of the images of people are taken with the person in the center of the image. And the person usually tends to occupy a large portion of the image itself. Whereas for the synthetic data, we can see that the people are spawned everywhere in the scene, and they stretch more to the edges compared with the real data set. Next slide, please. So there are a few insights that we can learn from the synthetic data set we generate. Not only do we get more boxes per image, this is because human annotators are lazy, so they don't want to annotate lots of people. If they're too close to one another, if they're too small to distinguish, it's a very tedious and difficult task for them to annotate all people in the image. So we get more consistency of labeling. We also get larger boxes per images with our data set. And also more key points are annotated per box. So you can see that on the left lower plot, we have almost all of our boxes have 17 key points annotated. And the ones that don't are usually the ones that the person is slightly out of frame or is occluded by another object or another person. That's why you don't have all the key points annotated there. Whereas for COCO, you have the largest number of boxes in the images don't have key points annotated for them. Also, for all the 17 COCO key points, our data set is more consistent. So you consistently get all the key points annotated for the synthetic data. Whereas for COCO, mostly the torso is annotated. So left shoulder, right shoulder, left hip, and right hip. Next slide, please. So with the animation diversity that we are able to pose our characters with, we are able to obtain a larger set of poses or more diverse set of poses in our data set. How do we quantify this? If you were to look at the representative key points of a human, so imagine a Vitruvian man frame that is extending its arms out, its legs out. The outermost key points are the wrists, the knee, the ankles, and also the nose. So we expect these key points to have the largest amount of rotation and translation in the image frame. If you look at, for instance, the nose on the COCO data set, you can see a footprint that extends from the left to the right. And it's mostly focused in the center because most people in the COCO data set are looking at the camera dead on or are in the frontal view. Whereas for the synthetic data set, we see interestingly that the nose tends to follow a horseshoe pattern. This is because some of our people have really strange poses. People are doing breakdance or they're flipping backwards, doing all sorts of weird things, whereas it's very difficult to obtain such poses from real world data sets. Same thing for the wrists and ankles. And a good thing that we can observe here is that our pose heat map encompasses the pose heat map of COCO. So we're already seeing the pose diversity of COCO, and we're able to obtain even more cases. And perhaps this helps us address some edge cases within the real data. Next slide, please. So we used a Detectron-2 Keypoint RCNN network with a Resonance 50 FPN backbone. We train models from scratch on real and synthetic data. That means we start from randomly initialized weights, and we take our real data, we train the network with that until it converges. We do the same thing also with the synthetic data, and we wait until convergence. We also do sim to real, which means we take the models that were trained on synthetic data, we fine tune them on real data sets. In both cases, we use different subsets of data, both for synthetic and real. This helps us to understand how varying sizes of real data and synthetic data affect performance of models. And finally, we perform evaluation on real data. Next slide, please. So here you can see the effect of using different sizes of synthetic data used for pre-training and also using different sizes of real-world data set. So on the left, so both of these plots show Keypoint AP, Keypoint average precision. On the left, we show the validation set from COCO, and on the right, we show the test set from COCO. For the test set, we don't have access to ground truth, so you have to upload this to the COCO challenge and obtain these metrics. Next slide, please. So I'm going to explain what these curves actually mean. So the blue curve at the bottom is using no real world images. So this is basically taking different sizes of synthetic data, training the models from scratch on that, and then testing on real domain. And what we can immediately see is that the Keypoint average precision is quite bad. So the zero-shot performance is pretty bad. But don't let this discourage you, because what we can observe immediately is that as soon as you start using the smallest amount of real-world data set, such as 1% of COCO, which is 641 images, you tend to see a large boost in performance. So the points that I've delineated with arrows show show the models that were trained from scratch on COCO dataset only, so using zero synthetic data. And as you can see, when you start using synthetic data, the curves tend to go up. So two trends are obvious here. Firstly, when you use more real data for fine-tuning, the performance tends to get boosted. That's no surprise. What's even more exciting is that when you use larger and larger amounts of synthetic data for pre-training, you see more and more boosts. And then the performance tends to saturate towards the end. This could be due to just saturating the model capacity itself as well. Next slide, please. So here are the numbers for the curves that I just showed you. And you can see for the bounding box AP and Keypoint AP, we get a huge delta over training from scratch, and also a huge delta over training from Imagenet pre-trained weights. So for the Imagenet tests, we would take a Imagenet pre-trained backbone and we fine-tune that on real data. So what this tells us is that if you are trying to solve a domain-specific task, such as a human keypoint detection or person detection, it's probably better to use a synthetic data that's tuned for detecting people, detecting humans, rather than using a universal generalist such as the Imagenet backbone. Of course, Imagenet is a very useful data set. It's expedited research a lot in the past few years, but we think that for doing domain-specific tasks, synthetic data set that is designed for your domain can help you gain even larger boosts. Next slide, please. And this is the test set from COCO on the Keypoint challenge. And we can see the same kind of trends here as well. In limited data regimens, we see a huge performance boost when we use synthetic pre-training. As you increase the size of real data, the boosts are smaller, but still a positive delta. So that's very encouraging. And what does that mean qualitatively? If you were to look at the 10% of COCO used for fine-tuning, the Imagenet pre-training backbone has some false positives shown in the top row, where random objects or random animals are mistaken for people. Zebras, for example, they're mistaken for people, whereas these mistakes tend to disappear when you use synthetic pre-training. Next slide, please. And also, one other thing that we observe is that when you do detect these people correctly, the keypoint detection accuracy and also bounding box detection accuracy tends to increase. So we get tighter boxes and better skeletal structure for people.
All right. Quickly, I just want to run through just a bit of the concepts around synthetic data generators and how we approach these. So I think one thing which is a bit of revisiting some stuff we talked about is what we're finding is that optimal synthetic data strategies is not about trying to just think about the way you collect real world data and exactly replicate the same strategy. Again, we have a superpower with synthetic data, which is we can generate so much of it programmatically, and we get to control diversity in ways that are a little bit more difficult to in the real world. So we use that as a starting point. We want to start with really high, focus much more on the diversity, and then focus more on domain adaptation and trying to make better and better, let's call them targeted data sets, or transforming those data sets into things closer to your real data. Important parts are, hey, define your problems. Like, what am I predicting? What distributions do I know that I need? And what things am I not completely certain? Because a lot of times it's what we're finding is, hey, if we just start with the very first experiment that we might do with a customer, or first one or two experiments, is just starting with the things that are the absolute minimum of we know we must do this. And then build from there. You actually end up learning a lot about how your model behaves with different types of data by approaching it that way. You kind of test some of the limits of it, and just generally, how does it behave under different conditions with different variables at play. And then we build a data generator. One really important thing to note with synthetic data is it in itself, like model training, is a set of experiments that have to be run. So the goal is not actually just to build a synthetic data set. The goal is to build some sort of parametric data generator such that you give yourself enough dials and controls, distributions to play with, such that you can do a number of different experiments and try to arrive at the best, sometimes refer to these as data hyperparameters. A data generator in our world of real-time 3D looks like this. It is assets, what we would call a sensor and labeler. Those two in the world of real-time 3D are kind of the same thing. It really just means your renderer. And randomizers. And once we've put that together, what we effectively have is a data generator that can come in the form of like an executable. It can be a container. It can be an API. It can be something you request from a web front end. We actually have all of those things. We've done them in different ways depending on the use case and what we're connecting it with. That data generator spits out data and allows us to do experiments. We also build these in a way that from day one scales in the cloud, because we want to start knowing that we may start with small data sets, but ultimately to be successful, likely we're going to need large amounts of the synthetic data to really get the power, to extract the power out of it. So we set everything up to be run in the cloud and scaled out. Let's talk about assets for a moment. I show some examples here of what digital assets are. All of these are synthetic images from Unity. So at the top right, you've got some animated cat models. And on the bottom, you see actually dogs in homes. There actually has been some use cases around pet detection that we have done inside of home environments. And so we actually have a compositional system with Unity that allows us to take these loose assets and put them into environments that themselves are actually randomized and procedural. I'm not going to show a demo in this particular meeting of this, but this home you see on the bottom right, we actually do things like material structures. We can randomize the lighting and time of day conditions, camera orientations. That's a fully randomized house, if you will. On the left, you actually see sort of a different type of randomization, which is like, we actually have digital twins of specific grocery type items that we have recreated via some scanning techniques. And they now exist inside of a, kind of virtual grocery shelf. And we can create kind of an unlimited set of diversity. Notice how in some cases, like in the bottom left, we've even flipped the object around a little bit. All this stuff is very easy once we've got the assets in place. Okay. Really quick on asset sourcing. There's multiple ways that we can source assets, or anybody using a real-time 3D engine or content creation tool can source them. Artist modeling, you could use something like photogrammetry. Also, you could just actually build a 3D shape. We use a flatbed scanner, scan all sides of the object. Let's say it's a box, and we've done this for retail objects. And then we create that object in 3D just with the scanned images slapped on top of the box itself, okay? In some cases, we actually use some procedural or parameterized asset models, right? Using a procedural generation system. There was a bit of that in the human models that Saleh showed. We actually have a lot more going on internally around this, especially around humans. Don't have anything to show today, but there's a fairly sizable investment going on there to really get high diversity around human assets. One of the other assets that Unity has, no pun intended, is the Unity Asset Store, where we and the community can access a very large amount of 3D objects that have kind of been contributed by the community. We have actually used some things from the Unity Asset Store developed by our community of developers and pulled those in, purchased those ourselves and pulled those into what we do as dataset projects. They are very useful. Obviously, you kind of have, just like the iOS App Store or Apple's App Store, you get kind of a range of quality on them. However, we do actually find that just having such a large collection, there's actually some very interesting stuff we can get there and really bootstrap these synthetic data projects. Sensors and labels. So we actually have a tool set that we have built that kind of enables us to easily attach labels to these objects and set up a labeling configuration. I won't run through this entire UI, but you kind of can get the idea of like how we configure these things in Unity. You saw Saleh present this. This is an example of randomizers. So now we're talking about the randomizers part of this and the configuration. We can apply different types of randomizers depending on the type of project we're doing. And these really, again, are your data hyperparameters. These are the things where when we make these, we want to build the data generator in such a way that all of these are exposed parameters. We may have a particular default distribution, but they're all parameterizable. And so, anybody can override these with the config file by requesting new data sets. This is some of the ones for people sans people. That home generation system that I talked about earlier, you can see just a very quick overview of some of the types of things we vary there and we provide an interface for. On the right, we actually have a different view. This is actually taken from the Unity editor when we're doing our data generator development internally. This is us creating a different set of randomizers specifically around object detection, like background object placement, randomizing textures and things like this. So this just kind of gives you a sense of like how we can configure different things and then how they can actually be adjusted and modified. And then just real quick through just some common questions that we often hear from engaging the community, engaging our customers. Any question that you can think of that involves word photorealism ray tracing. This one comes up all the time. Generally, the question is along the lines of, okay, awesome. Can I need highly photorealistic images or do you guys like have ray tracing support and stuff like this? The answer is yes, Unity supports ray tracing. It's a bit harder to get set up and configure. We do support it. On the topic of photorealism, again, it ends up that tends to be like the starting point. We want to start with creating their data set as close to the domain of the real world data that they're looking at. There's a cost associated with getting things to work well, to look photorealistic, and for really physical based lighting like ray tracing, there's a cost to getting that working well. It is not just a cost in setting up your environment, it is also a cost in having good assets that have good materials and textures, because this is really where you'll start to see the problems with poorly done materials. So you're really looking at like, you can get to that point of photorealism, but at what's it going to cost you to get there? We often find that, if your starting point, kind of as Lee was showing, is like, I have a small amount of real data. Sometimes a really good starting point is, let's get, maybe not photorealistic, but let's get pretty good on the lighting and some of the other conditions and pretty good on realism. and focus on a lot of diversity. And then let's start to build more from there. Let's get more realistic as we go. And let's see if adding that realism helps. And then how much do we need to add? And how much data do we need that is photorealistic? Approaching it that way really allows us to test out kind of incrementally. Like when I do this, when I do this much extra work on my synthetic data, am I actually getting the returns that I really need for my application out of it? And that's really important. Sometimes there are questions about, things around anything around data augmentation. So isn't it just easier to use data augmentation? We've had customers evaluating creating synthetic data with a real-time 3D engine versus just compositing, 2D imagery onto more other 2D imagery. In general, still, this is still a very valid approach. It's been used for a very long time, and does get you so far. All of these strategies, when working together, generally work well together. But it's really not that one is particularly superior to the other. We're finding, things like, hey, given that we can create a whole 3D environment, we have some advantages over augmentation because you end up with what I would call almost like 3D data augmentations, where we do things, but we perturb the scenes in ways that are actually semi-physically accurate. They may be unrealistic, but they're physically accurate, right? And for instance, lighting remains consistent, or things like that, which is, we do see that as one as important. Another one that comes up is on the use of GANs for domain adaptation. I would call this an open research area. There is a lot of literature coming out on this. They have their challenges. We have both had customers apply. We've had customers apply GANs on top of synthetic data we've given them, and we've seen it work and we've seen it not work. So it's not really a silver bullet, and there are some challenges because you actually are layering some ML-based technologies on top of each other here. So just know that this is really an active research area. So there's no clear yes, this is the silver bullet for how you do this. So. And with that, I'll just quickly summarize by saying, as you can see, at Unity, we really are embracing data-centric AI. We believe that working on the data and iterating on the data is really enabling customers to have much more robust, well-performing models in the real world. And we're trying to provide as many tools as we can for customers to really get full experimentation over their data, starting with synthetic data. And with that, I think we are done and can cut over to questions.
You want to take the first question, Alex?
I haven't actually
Where
looked the window.
Best place to start for beginners?
Where would be the best? Beginners, is this beginner for, as in, where should we start in terms of how do we try to make use of synthetic data, or how do we get started with synthetic data? There's actually there's a couple starting points. One thing we've done is we actually put some tutorials out about how you can actually create synthetic data in Unity. I think we can send maybe some links to that after the webinar.
Can we drop GitHub into the form?
Yeah, I'll have to copy paste it just because feel free to go do that. I have to.
Yeah,
am I still sharing? Am I sharing my screen currently, or am I not?
I think Andy took it back from you.
Ah, great. Okay, yeah. When I'm not talking, I will drop it into the form here. Additionally, and you can see this on our products page. This is that particular package. We have a package in Unity that helps you build a data generator inside of Unity. It does simplify the process. There is still a lot of work around curating 3D assets, things like this. We also ourselves offer building data generators for others and enabling them to do experimentation. themselves. We have an offering around that, and so that's another place to get started. We usually, when we interact with customers on that regard, we do kind of a deep dive a bit on the particular target problem and try to come up with a data generation strategy that'll work best for your use case and some experiments to run. So we really see ourselves as partners on that journey with you. And yeah, I'll drop that in just a bit. Okay, what sort of percentage between real and synthetic is a good starting point? Salehi, do you want to, Salehi, sorry, do you want to take that one?
Sure. So what we have seen with our synthetic data training so far is that using as large a synthetic data set as you can is usually beneficial. So as I showed with the plots, you could see that the curve still went up as you increased the size of the synthetic data. And then at some point it started to saturate. So roughly at around 250,000 synthetic images is where we start to see the most amount of benefit, usually with our synthetic pre-training, with varying sizes of real data. So it doesn't matter how much real data you have. What really matters is to be able to complement the real data sets you have, and really be able to obtain the edge cases that are not so common in the real data set with the synthetic data. So that's how I think synthetic data can complement your real data sets. And one other thing that I should also mention is that generating 10 synthetic images with labels is as easy as generating 1 million synthetic images with labels, because the labeling comes for free and the data generator, you could just let it run. So if you have time to wait for it to generate, and these data generators tend to be quite fast, so you can expect to generate maybe 1 million images in 6 hours or so, as we have done internally as well.
Just a reminder, the survey link in the chat window. We appreciate your feedback to help better guide our content from week to week. And also, if you would like to go into the draw to win a Unity prize pack, please include your email address at the end of that survey form. And some more questions there to answer.
So there's a question about, what's that?
Yep, go ahead.
Yep. So there's a question about video. I was actually hoping I was going to get this question. Absolutely. Video's high priority on our roadmap. We don't have something to show today for this. But as you can imagine, one of Unity's biggest strengths is it is a real-time 3D engine, meaning we also support physics, like real animations, and it is a game engine. It's made for games, right? As such, video is actually something we do relatively well. When we started kind of on this venture of synthetic data, we wanted to really get some of the foundations around static imagery right before we got into video, because video introduces another set of challenges in many ways actually around data hyperparameters, because now you start to get into like defining the what are the randomized dynamics in the scene and things like this. And we want to make sure we got the other aspects of right. This one's on our roadmap. It is high priority, and we do know that this is one where we are seeing folks more and more try to train on video data for obvious reasons. There's more information in video, temporal information, right? So we're going there. So stay tuned, and hopefully in one of our future webinars, we'll have a cool demo to show there as well, and some use cases. So
awesome. If there's no other questions, maybe we'll hang around for 10, 20 seconds, see if anyone else pings us. But in the meantime, I'd love to thank all of our speakers today. Super interesting area of technology that many industries and companies are starting to venture down, and Unity, as always, is at the forefront of these technologies. And if you'd like to hear more about computer vision or anything else in our AI, machine learning, and 3D propositions, please sign up to our social media channel. The links are in the chat window, And as always, there's no more questions for today. I think that's it for our webinar today, and we look forward to seeing you.
I would give one more plug, Andy, if you don't mind me jumping in here at the end.
Go ahead.
So we do have, there's some questions about where to start as a beginner. What else can you see? I think there's some questions about working in Unity as well. We actually do have an event coming up in about, 2 weeks, actually. It's called the Unity AI Summit. I'll post a link in the chat as well. There will be multiple sessions talking about all things related to AI, including some of the work that we're doing in computer vision. And I believe, Alex, there are a couple of workshops, correct, for the AI Summit? We're talking about computer vision.
So in the AI Summit, yeah, there are a few workshops. One of the ones we are doing will actually be a training and object detection model using synthetic data from one of our tools. If you saw the image in the bottom right of one of the slides I showed, you saw a dog sitting around a house. We're actually doing a dog detection inside of, like a pet detection inside of home environment, hands-on lab. So it'll involve training a model that we will give with synthetic data, and we'll kind of walk you through that and also the data generation process a bit.
And those sessions will be recorded. They may not be the most time appropriate given the wide range of time zones that I think we're touching today, but they'll be available on recording, as well as if you have questions, I'm sure we can figure out how to get answers to those questions.
Yeah, I think this may be about today's webinar. Yes, as always, if you've registered with us to be in this webinar and attended via Zoom, you will be emailed a recording of today's session early next week. Awesome. Thank you guys for joining. I realize it's very late in your time zone there. Our audience in South APAC really appreciate your time to address our audience today. Thank you everyone for attending. See you next week.